linearly independent. So we just apply induction on n. Okay? Apply induction on n. So n equal to one case. N equal to one case is clear, because if AV equal to lambda V is a non-zero vector, and lambda is some eigenvalue. A non-zero vector by itself is always linearly independent. Yeah, a non-zero vector is always linearly independent by itself. So the proposition is clear for one eigenvalue. Yeah, for one eigenvalue, because eigenvector is always a non-zero vector. So by itself it is linearly independent. And suppose we have proved that the statement is true for n-1 distinct eigenvalues. Yeah, if I take n-1 distinct eigenvalues and corresponding eigenvectors, we can now assume that they are linearly independent. And now we prove the proposition for n. Yeah? So suppose I have these vectors which are corresponding to distinct eigenvalues, these eigenvectors, and suppose they are linearly dependent. That means there is a linear combination which is equal to 0. Yeah? So now I apply my linear transformation to this equation. If I apply linear transformation to this equation, then I get C1 TV1. TV1 V1 is eigenvector with eigenvalue lambda 1. So when I apply T to this, I get C1 lambda 1 V1. When I apply T to C2 V2, I get C2 lambda 2 V2, etc. If I apply T to Cn Vn, then I get Cn Vn Vn lambda n. So this equation gives me this. Yeah. So I have these two equations, 1 and 2, and I try to eliminate V1 so that I can apply induction. So in order to eliminate V1, I have this C1 V1 in the first equation, C1 lambda 1 V1 in the second equation. So I multiply this by lambda 1 everywhere, yeah, and then subtract, and that we will get rid of V1. So 2 minus lambda 1 times 1 gives me this equation, C2 lambda 2 minus lambda 1 V2, Cn lambda n minus lambda 1 Vn equal to 0. But this is non-zero because lambda i's are distinct. This is non-zero, right? And this C2 is a scalar that we want to prove that it is equal to 0. But when I multiply a eigenvector with a non-zero scalar, I get an eigenvector. Yeah, because if TV equal to lambda V, then T of alpha V is also lambda alpha V because T is linear. So any scalar multiple of an eigenvector is eigenvector of this with same eigenvalue. So lambda 2 minus lambda 1 times V2 is an eigenvector. I mean, it is a multiple of V2. It's a multiple of V2. So this is an eigenvector with eigenvalue lambda 2. Similarly, lambda n minus lambda 1 Vn is an eigenvector with eigenvalue lambda n. But lambda 2, lambda n are distinct, and these are eigenvectors. So by induction, I get that all the Ci's are 0. C2, C3, Cn are 0. But when C2, C3, Cn are 0, then C1, V1 equal to 0. But V1 is a non-zero vector, so it will give me C1 is also 0. Okay. So we have proved that eigenvectors corresponding to distinct eigenvalues are linearly independent always. And now go back to the exponential functions. We know that if I differentiate e to the power lambda x, I get lambda times e to the power lambda x. So the exponential function is eigenvector with eigenvalue lambda. So if I take e to the power lambda 1x, e to the power lambda nx, these are all functions inside the vector space of smooth functions. V is the vector space of smooth functions, and the differentiation is the linear operator, and e to the power lambda x map to lambda times e to the power lambda x. So e to the power lambda x is eigenvector with eigenvalue lambda. So e to the power lambda 1x, e to the power lambda nx, these are eigenvectors corresponding to distinct eigenvalues lambda 1, lambda 2, lambda n. So by this earlier proposition, they are linearly independent. These functions are linearly independent. Okay. This we have proved before by using limits. Okay. We applied induction, but now the same fact we have proved by using the fact that eigenvectors corresponding to distinct eigenvalues are linearly independent. So these n eigenfunctions, e to the power lambda 1x, e to the power lambda 2x, etc., these are linearly independent functions. Okay. And lambda 1 lambda 2, lambda n are distinct real numbers. I can take any arbitrary large sequence of distinct real numbers, 1, 2, 3, 4, etc., etc. So inside the vector space of all the smooth functions, I have sets which are arbitrarily large, linearly independent sets. Yeah? So dimension of the vector space of smooth function is not finite. It is an infinite dimensional vector space, because we can keep on producing functions which are linearly independent, bigger and bigger sets of functions which are linearly independent, namely e to the power lambda 1x, e to the power lambda 2x, etc., etc. Okay, all right. So this way we understand a concept which is arising in matrix theory can be applied to the vector space of functions. Okay, and the same concept gives a new property of these exponential functions, that these exponential functions are all linearly independent. Okay, now let me define what are diagonalizable matrices and diagonalizable linear operators. Okay, so suppose I have a finite dimensional vector space. This will be my assumption most of the time, although my example that I just discussed was a infinite dimensional vector space over the field of real numbers, namely the vector space of all smooth functions is infinite dimensional. But to define many concepts in linear algebra, we work with finite dimensional vector space like Rn or Cn, etc. Okay, so take a finite dimensional vector space over a field of scalars, and suppose this T is a linear operator. We say T is diagonalizable if there exists a basis consisting of eigenvectors of T. Yeah? If there is a basis of the vector space which consists of eigenvectors of T. Yeah. So, for example, I take the vector space which is linear span of e to the x and e to the 2x. Yeah. I just look at this vector space, the linear span of e to the x, e to the 2x. These are two linearly independent functions. So dimension of v is 2. And t is acting on v. And t of e to the x is equal to e to the x. If t is the differentiation operator. T is the differentiation operator, dx, and t of e to the 2x is 2e to the 2x. Okay, so 2 is an eigenvalue, 1 is an eigenvalue. Okay, 1 is an eigenvalue, 2 is an eigenvalue. So, but these two functions are linearly independent. So I have a basis of eigenvectors corresponding to distinct eigenvalues 1 and 2. These are linearly independent. Dimension of v is 2, and therefore differentiation operator acting on this vector space is a diagonalizable operator. T is called diagonalizable if there is a basis of eigenvectors of v. Okay, so suppose B is an ordered basis of eigenvectors, and TVI equal to lambda I VI. Yeah, eigenvalues could be distinct, but I have a basis of eigenvectors of the vector space. Then we say that the linear operator is diagonalizable. Okay, then if with respect to this basis, if I write the matrix, it will be a diagonal matrix because TV1 is lambda 1 V1, TV2 is lambda 2 V2, etc., etc. So if my basis consists of V1 up to Vn, then the matrix of this linear operator with respect to this basis of eigenvectors is the diagonal matrix. Yeah. So I can then convert this matrix into matrix of any other basis. Then it will be a similar matrix. This matrix will be similar to the matrix of T with respect to some other basis. Yeah. So an n by n matrix, we copy the definition to matrices. N by n matrix over a field of scalars is said to be diagonalizable if the corresponding linear transformation TA given by TAV equal to AV, where V belongs to Fn, is a diagonalizable linear operator. So matrices are diagonalizable if there exists a basis of eigenvectors. The eigenvalues, we are not saying anything about the eigenvalues. If there is a basis of eigenvectors, then of a given matrix, n by n matrix, then we say that A is a diagonalizable matrix. The only condition is that the eigenvalues have to be taken in the field of scalars. Yeah, eigenvalues have to be taken in the field of scalars, and there are real matrices which have no eigenvalues at all. We will soon see an example. So if you have eigenvalues in your field of scalars and you come across a basis of eigenvectors, then we say the matrix is diagonalizable or the linear transformation is diagonalizable if there is a basis of eigenvectors of the linear transformation. Yeah. So let us prove that an n by n matrix A over a field of scalars is diagonalizable if and only if there is an invertible matrix, so that P inverse AP is a diagonal matrix for some invertible matrix. Yeah. So the given matrix is similar to a diagonal matrix, then there is going to be a basis of eigenvectors if and only if there is a basis of eigenvectors, then there is going to be a matrix P which is invertible, so that P inverse AP is a diagonal matrix. So A becomes similar to a diagonal matrix. Yeah. Under similarity transformation, the rank doesn't change because rank of a matrix times invertible matrix is same. Similarly, P inverse AP will have same trace also. Yeah. So we'll prove these facts very soon. But let us see that our definition of diagonalizable matrix can be detected. A matrix is diagonalizable if and only if it is similar to a diagonal matrix. Okay, it is similar to a diagonal matrix. So, and in that case, the column vectors of this invertible matrix are eigenvectors of A. And when I take this diagonal matrix, the diagonal entries are eigenvectors, eigenvalues corresponding to the eigenvectors. Okay, so let us see that. This is a very important observation. How do we get hold of eigenvectors? Okay. How do we get hold of eigenvectors and eigenvalues? So if we find a matrix which is similar to A, and that similar matrix is diagonalizable, it is a diagonal matrix, then the entries on the diagonal are eigenvalues and the column vectors of P are eigenvectors. Okay, so suppose A is a diagonalizable matrix. That means there is a basis of eigenvectors. There is a basis of eigenvectors of this matrix TAVI. TAVI is AVI equal to lambda I VI. That's the meaning of A being diagonalizable, that we have a basis of eigenvectors, and suppose eigenvalues are AI, lambda I for I equal to 1 up to n. Yeah. So now let us make this matrix P whose column vectors are eigenvectors, and the matrix is diagonalizable. That means this V1 up to Vn is chosen to be a basis of Fn, and so these are linearly independent vectors and they live inside Fn. So this is n by n matrix whose column vectors are linearly independent. That means the column rank is n. So the nullity is 0, and therefore it is an invertible matrix. This matrix P whose column vectors are eigenvectors which are linearly independent is an invertible matrix, and suppose D is the diagonal matrix, then look at A times P. Okay, A times P I can multiply by using the column vector formula. It is I display the column vectors of P, then A times V1, V2, Vn is lambda 1 V1 because this is equal to AV1, and this is AV2, AV2. This is AVn. Okay, so it is lambda 1 V1, lambda 2 V2, lambda n Vn. So this matrix P is being transformed into another matrix where the column vectors of P are being multiplied by lambda 1, lambda 2, lambda n. First column vector I am multiplying by lambda 1, second column vector I am multiplying lambda 2, and so on. But this is equal to P times D. This matrix is really P times D, where D is the diagonal matrix, lambda 1, lambda n. Okay, so look at this equation. A times P is equal to P times D. So if I have a basis of eigenvectors with eigenvalues lambda 1 up to lambda n, then I make this diagonal matrix D, whose diagonal entries are lambda 1 up to lambda n, and the matrix P is the matrix whose column vectors are eigenvectors, and they are arranged in the same order. Okay, V1 up to Vn are the column vectors, then the eigenvalues lambda 1, lambda 2, lambda n go into the diagonal of D. So if AP equal to PD and this P matrix is invertible, then P inverse AP is equal to D. So A is similar to D, right? So if the matrix is diagonalizable, it is similar to a diagonal matrix, and the diagonal entries are the eigenvalues by construction. Okay. So let's now look at the converse. Conversely, suppose my matrix is similar to a diagonal matrix where the entries of the diagonal matrix are in the field of scalars. They are in the field of scalars. Then and P inverse AP is this diagonal matrix. That P inverse AP equal to D implies that AP is equal to PD. So display the column vectors of P, and that says that A times P is equal to A times V1 up to Vn. That is lambda 1 V1, lambda 2 V2, lambda n Vn. This is equal to PD, and this says that Vi's are eigenvectors. Vi, AVI is lambda I Vi. Okay. So if A is similar to a diagonal matrix whose diagonal entries are in the field of scalars, then the column vectors of P are the eigenvectors and eigenvalues are lambda I. Okay, so we have proved this fact that a matrix is diagonalizable if and only if there is a matrix P of whose column vectors are eigenvectors, and this matrix P is invertible and P inverse AP is D. Okay. Let us notice that if I change my matrix A to a matrix B by this transformation P inverse AP, that I get a similar matrix. P inverse AP is called a matrix similar to A. Then the characteristic polynomial of A and B are equal. Similar matrices have same characteristic polynomial, okay. And therefore they will have same set of eigenvalues also counted with multiplicity, because eigenvalues are roots of characteristic polynomial which are lying in the field of scalars. Okay. So let us show that similar matrices have same characteristic polynomial. So what is the characteristic polynomial of B? It is determinant of xi minus P inverse A. Earlier I wrote determinant of A minus lambda I, okay, as the characteristic polynomial of this matrix lambda, but I can just write lambda I minus P also. This will differ from this characteristic polynomial simply by a negative sign. If the degree is odd, then we will acquire a negative sign, but the roots don't change. So very often we write the characteristic polynomial of the given matrix B as xi times this matrix B. Okay, I is the identity matrix, but xi can be written as P inverse times xi times P, and so I can write determinant of P inverse times xi minus times P, but this is determinant of P inverse. Determinant is multiplicative. This is determinant of xi minus A. This is determinant of P. These two multiply to 1, and I get determinant of xi minus A, which is the characteristic polynomial of A. Okay. So by changing my matrix to a similar matrix, I don't change the characteristic polynomial. Okay. So if a matrix is similar to a diagonal matrix, then this shows that the characteristic polynomial will have roots which are diagonal entries of the matrix, because the characteristic polynomial of a diagonal matrix is simply lambda I minus x, product of all the lambda I minus x, where lambda i's are the diagonal entries. Okay, so similar matrices have same characteristic polynomial.